Today we're going to talk about Raman spectroscopy with some practical applications. So it's going to be a little bit of a survey of introductory survey, if you will, to Raman spectroscopy as applied to different kinds of materials. And behind those materials, if you will, are the applications, which I'd like you to be thinking about. Our talk today is going to cover these topics. First, we'll have sort of a brief overview of Raman spectroscopy and photoluminescence. I like to point out to people that with a Raman spectrometer, and in particular micro Raman spectrometer, you're capable of doing both Raman spectroscopy and photoluminescence spectroscopy with the same instrument. So it's basically a two-in-one instrument. And that's where we get into fluorescence or photoluminescence as friend or foe. So we'll talk about that a little bit. Then we'll cover polymorphism and the ability of Raman spectroscopy to distinguish and differentiate different crystal forms. We'll talk about liquid and headspace Raman spectroscopy, and doing this by putting an attachment on a micro Raman spectrometer. So this can be done even with an instrument that's ostensibly a micro Raman instrument. We'll talk about the Raman spectroscopy of polymers, and then finish with a discussion of particle size characterization with chemical specific identification. So Raman spectroscopy is a vibrational spectroscopy. Most people are familiar with infrared absorption as a vibrational spectroscopy, but Raman spectroscopy is also a vibrational spectroscopy. And both of them, of course, are a result or are based upon the study of materials through the interaction of light with molecules or compounds such as covalent solids, ionic solids, that sort of thing. Now, what distinguishes these two very complementary methods? Infrared spectroscopy involves an absorption of a photon to drive the molecule from the ground to the first excited vibrational state. Raman spectroscopy, as we'll see in the next slide, involves light of, in principle, almost any wavelength, but principally we use light throughout the visible. So there's no absorption involved, but what one sees is a scattering, and I'll describe that in the next slide. So applications of vibrational spectroscopy. Well, many of the applications for Raman are similar to, and as I've said, complementary to those of infrared spectroscopy. So you have, of course, molecular spectroscopy by Raman that you can do where you're studying essentially the vibrations of atoms, which is to say the chemical bonds within the molecules, and can study gas, liquid, or solid states. And in particular, solid state, that's tends to be an emphasis, particularly as you might imagine with a micro Raman instrument. You can certainly study molecular species, but you can also study molecular crystals. Now, molecular crystals are those such as, let's say, acetaminophen or aspirin, for example, right? Where you have a molecular species is the origin of the crystal. In contrast, you can have materials like silicon or titanium dioxide or zirconium dioxide where there is no molecule. And so those are frequently referred to as covalent solids, and then there are ionic solids. And of course, you can characterize gels as well. So crystalline, amorphous materials, gels. Raman spectroscopy is particularly useful for studying the solid state materials at least in one respect, because of the ease of sampling. All right, so here is what I call the obligatory energy diagram describing Raman scattering. So in the center, you see the energy diagram for Rayleigh scattering. And what you have is, let us say, the molecule originating in the ground electronic and ground vibrational state. And so if I use my mouse as a pointer here, so here's where the molecule starts out. And let's say we illuminate this sample. Let's say it's totally transparent in the visible, so we illuminate it with 532 nanometer light, And so the Rayleigh scattering that we see off of it is elastically scattered light, meaning there's no exchange of energy. And so the photons that are scattered are at the same wavelength, 532 nanometers. Now in Raman spectroscopy, you have both Stokes and anti-Stokes Raman spectroscopy, where the molecule originates in either the ground vibrational state or the first excited vibrational state. Now, at room temperature, the ground vibrational state is the one that's the most highly populated, and so 99%, let me say, of all Raman spectroscopy that's done is with the Stokes. So let's just focus on this. So we have, let's say we have a compound, it could be methanol in a vial, let's say, and so we shine a laser beam in there, let's say 532 nanometer light. We shine a laser beam into the methanol. There's no absorption, and so it doesn't reach the first electronic excited state. There's no absorption. But what happens is that the molecules can achieve what's called a virtual state, which can only really be described quantum mechanically. And upon that interaction of the first photon with the molecule, a second photon, so it's a 2-photon process, a second photon is scattered, and that second photon is scattered at an energy less than the incident photon, as you can see here. This photon, having given up a quantum of energy to the molecule, such that the molecule ends up in the first excited vibrational state. So the molecule starts here, it ends up here, and then the scattered photon has an energy of h nu of the excitation frequency minus the frequency of this vibrational quantum. And so if you then detect light at wavelengths longer than, let's say red shifted relative to the laser light, you'll see a spectrum, you'll see peaks associated with these kinds of transitions. So you can use a variety of excitation wavelengths to do Raman spectroscopy, and here is an example of that. So you're looking at 3 Raman spectra acquired from polystyrene at 3 different excitation wavelengths, 532, 638, and 785. And you see that they're plotted on a Raman shift scale with units that are the same as what you would observe in infrared absorption spectroscopy. Hence this complementarity, because you're probing the same kinds of transitions, I should say. Now, what you see here is that as I've moved from shorter to longer excitation wavelength, this background is diminishing. And what is this background? This background is a photoluminescence. Now, polystyrene is transparent, so it itself is not absorbing, but what is absorbing are, let's say additives or maybe even brighteners that are sometimes put in the industrial processes. And since fluorescence is so much more efficient than Raman scattering, it can be an interferent. Now, in this case, it's not so bad. In some cases, you can not see the Raman scattering at all because the fluorescence is so intense. And so if we plot these 3 spectra now on an absolute wavelength scale, what you see is that beginning with the 532 nanometer excitation, now maybe you can see a little more clearly this underlying tail of the emission of the photoluminescence that we're exciting at 532. And now to avoid that, we go to longer excitation wavelength at 638. Okay, that's good. We've reduced the photoluminescence. We haven't eliminated it, but we've reduced it. And finally, we go to an even longer excitation wavelength where we're no longer coupling into the absorption spectrum, the excitation manifold of whatever it is that's doing the absorbing and emitting. And so now we get a nice flat baseline spectrum at 785. So what do we see here? We see that the Raman bands are all shifted relative to the laser line. So all these sharp peaks here, they're basically the same, right, from the polystyrene. And they're always as a shift relative to the laser line, whereas the photoluminescence is always at an absolute wavelength. And as I said, in some instances, the photoluminescence can be so strong, so overwhelming that you don't even see the Raman bands because they're buried in the noise. Therein is the basis for people needing to select different lasers or excitation wavelengths for doing Raman spectroscopy. If it weren't for the problem of fluorescence, photoluminescence, one laser wavelength would be fine. But here is an example of the problem of photoluminescence, and also sort of a tip for those of you who may already be doing Raman spectroscopy, and in particular are working doing micro Raman with transparent materials. I'll explain in a moment why that's important. So here are Raman spectra of a glass microscope slide excited at 532, 638, and 785 nanometer excitation. So at 532, great. Not much photoluminescence at all, maybe a little bit out here, but basically what we're seeing is the Raman scattering of the glass, the SiO2 that makes up essentially SiO2. I mean, there are different structures, but that's essentially what we're looking at from a glass microscope slide. Great. But if we go to 638 nanometer excitation, now we're starting to get a lot of photoluminescence, which we've excited. So in this case, it's working the opposite for us. We go to longer excitation wavelength, and because of the nature of glass, we get more photoluminescence as we go to redder wavelengths, just the opposite of what we were seeing with the polystyrene. So now you can still see a little bit of the Raman scattering, but it's really weak relative to the photoluminescence. And here at 785, you can barely see the Raman scattering compared to the very intense photoluminescence out in this very important region, between at least from 1,000 beyond 2,000 in the fingerprint region. Now, I say this is very important. Why? Because, well, for a lot of people who might be working with biological samples, they're typically using glass microscope slides, and they're doing their imaging with either reflected or transmitted white light. Those materials themselves, say biological cells, they're transparent, and they will often fluoresce at shorter excitation wavelengths, so they choose 785 nanometer excitation. But it's not wise to analyze those kinds of materials on a glass microscope slide because of all this photoluminescence, you see? So the laser is going to penetrate the material. So if the material is opaque, none of this is relevant, right? Because the laser won't pass through it. But if the materials are transparent, then because of the, particularly if the samples are thin path length, let's just say, then the substrate, which is so much thicker, is going to contribute substantially to that signal. So here's a tip for you then. If you're working with thin films, could be thin transparent polymers, could be biological cells, any number of optically transparent thin materials, and you need to use red excitation to avoid the photoluminescence from your samples, then I strongly recommend you get a hold of fused quartz substrates for the reasons that you see here. These are from GM Associates, and you see exciting at 532, 638, 785, wonderful results. All we see is the Raman scattering from the fused quartz and no photoluminescence. So this is the ideal substrate if you're working with thin transparent films or biological materials that pass the light, particularly if you're using 785 nanometer excitation, then you'll have very little background contribution from your substrate. So think fused quartz. All right, now that was photoluminescence as foe. Now let's look at it as friend. Here are spectra of the same sample, same location actually, of what's called few layer molybdenum disulfide. That's an exfoliated sample of what are also known as 2D crystals. So what you see are spectra, and I just say spectra because the spectra consist of both Raman scattering, Raman bands, and photoluminescence bands, right? And we're exciting at both 532, 633, and so the Raman bands occur as if we're plotting on an absolute wavelength scale, the Raman bands then appear at an absolute wavelength that's, of course, always shifted relative to the laser line, which would say be around here for 633 and somewhere over here for 532. So the Raman bands are always shifts on a Raman shift scale. They appear at different wavelengths at an absolute wavelength scale. Conversely, the photoluminescence, being an emission, occurs at the same absolute wavelength, irrespective of the excitation that you're using, as long as you're able to couple in to that same absorption. All right. So what does this demonstrate? This demonstrates that with a Raman spectrometer, you can, with the same instrument, if the photoluminescence and the Raman scattering are sufficiently separated, you can do both, quite frankly, with the same spectrometer, do photoluminescence and Raman spectroscopy. Now here's another example of that as well. Here we see Raman spectra, I'll call them that because we're plotting them Raman shift scale here, of corundum, aluminum oxide, that has chromium in it as either a dopant or an impurity. And chromium is generally found in aluminum oxide, and it's very often found in the 3+ oxidation state. Now, we see the Raman bands, we can identify them because on a Raman shift scale, these bands at 144, 417, 568, 734, they appear at the same Raman shifts, irrespective of what excitation wavelength I use. However, these two peaks labeled PL for photoluminescence, they only appear in the 633 nanometer excited spectra, but they're absent on the Raman shift scale in the 532. So this gives you a way, again, of identifying and differentiating Raman bands versus photoluminescence peaks, because these peaks appear at the same absolute wavelength. From the same samples, and now looking at absolute wavelength, now these are different peaks, you see the very well-known R1 and R2 peaks from chromium in the 3+ oxidation state in this sample. And again, this is acquired with a Raman spectrometer. And you see that for all three of these excitations, we're coupling into the transition, so you get these very sharp and intense emissions from the chromium. And in the inset, you can see how well resolved they are. And this is another point too about the Raman spectrometer for photoluminescence. Because the spectrometer is designed for spectral resolution for vibrational transitions, then it has very good spectral resolution to resolve very small or very narrow peaks in photoluminescence. So if you're looking at sharp emissions like from this transition metal, chromium, or even the lanthanides, then the Raman spectrometer will be able to resolve these very, very narrow peaks. In fact, in a slide coming up, I'll show you the in vapor phase Raman spectra, a full width half max of less than 1 reciprocal centimeter. That's kind of resolution that you can get. All right, so that's photoluminescence. So we're finished with our little discussion of photoluminescence for using a Raman spectrometer. Now let's just briefly cover some aspects of Raman spectroscopy. And so I show you the spectra of methanol and ethanol to simply, for those of you who are not, again, perhaps familiar with Raman spectroscopy, for you to be able to see that how sensitive it is to molecular structure, because here we have basically two alcohols that differ only by the one CH2 group here, right? So, and yet, look at how different the Raman spectra are. So Raman spectroscopy, just like infrared spectroscopy, is sensitive to chemical bonding and molecular structure through the vibrational modes. And you can see that clearly just in these spectra of methanol and ethanol. Now here's a case where you have The same chemical composition, same stoichiometry, but different molecular structures, glucose and fructose. Nevertheless, you can see in the upper left-hand corner that the spectra of each of these compounds can be readily differentiated by Raman spectroscopy. You can have similar, not identical, or not same stoichiometry, but similar molecular structures. These are two important compounds in the world of forensics, police forensics. So you've got MDMA on the left, and that's the blue spectrum, and methamphetamine. And if you just kind of look closely and kind of compare these spectra, all right, even if you don't have what I call the spectroscopist's eye, having looked at spectra for many, many years or decades, you can see the differences in the peak positions and relative intensities of these two compounds, even just in this low frequency region. So Raman spectroscopy can easily differentiate these two compounds where the difference in the structure is basically just this, this chemical moiety over here. You can also differentiate diastereomers. So here's ephedrine and pseudoephedrine, and so diastereomers, and differentiating them, how they are basically oriented in space, and these molecules. And you would expect that the spectra would be very similar, and indeed they are. However, they are not identical. And if you look closely at some of these bands, and I'm kind of pointing to some, you can see the differences in the relative intensities. And I'm sure that if we were to blow up these spectra, as we're going to see with polymorphs, we'd see some differences in the peak positions as well. Now, we've been talking about some organic. Now, here's one example of an inorganic compound, or two compounds very similar to each other. They're both sulfate salts. One is magnesium sulfate, one is sodium sulfate. And the band that we've blown up here is basically the symmetric stretch of the sulfate group. But notice how the peak position and even the width of that band is affected by the cation that's in this crystalline compound. So even if you have just a change in the cation in an inorganic compound, one can, by Raman spectroscopy, if you have a spectrometer with sufficient resolution, readily differentiate even these kinds of inorganic compounds. Carbon nanotubes. Now, these are of recent years, technologically important compounds. There's a lot of development being made in them for different purposes of strength, but also electronic properties. And the vibrational modes out in the fingerprint region can be correlated to, as you see here, the electronic properties, the G band. And the D band gives you information about information about the defects in the structures of these nanotubes. And the low frequency region allows you to determine the diameters of these nanotubes as well. So that by using Raman spectroscopy with access to the full spectrum, there's a lot that you can do to characterize nanotubes and the variation that you might find depending on how they're fabricated to produce different electronic properties, as well as the diameters of them. And I failed to mention that these modes down here in the low energy region are due to what are called the radial breathing modes. So if some of you are familiar with that, just know that those can be accessed fairly readily by Raman spectroscopy, perhaps not so easily by infrared. Okay, now let's talk about some applications, and specifically polymorphism. And so we'll discuss zirconium dioxide, titanium dioxide, and two forms of acetaminophen, or paracetamol, as it's also known in the pharmaceutical industry. So the interesting thing is that Raman spectroscopy is so sensitive to crystal structure. So here you have, I always found this fascinating, quite frankly. I'm sort of a guy who I like group theory and crystallography and so forth. So I think this is actually fairly remarkable that you can use Raman spectroscopy in a fashion that's complementary to X-ray diffraction. Now, don't get me wrong. If you can do X-ray diffraction, by all means do it. But if you've got some kind of, let's say, uh, structures, devices, materials that, let's say, precludes you from using X-ray diffraction, and or you need the spatial resolution afforded by a micro Raman instrument, then I'm here to tell you today that you can use Raman spectroscopy in a manner complementary to X-ray diffraction to differentiate crystal forms, uh, uh, in particular polymorphs, and also different elemental forms as well. So at any rate, here you see clear differences in the monoclinic and tetragonal forms of zirconium dioxide. Here are two spectra obtained 532 nanometer excitation of anatase and rutile titanium dioxide. Same chemical compounds, but of different polymorphic forms. Identical chemical composition, different crystal structures. And so you can see from the band positions, in particular, say the bands right out here. So in the rutile, you've got 241, 445, 610, distinctly different from the bands that you see here in the anatase form of TiO2. So these two crystal forms can be readily differentiated. Now here, what I want to show you is, again, those two pure forms, if you will, of the rutile with and anatase. And this green spectrum is of a grain, a single grain, from a vial that was labeled as rutile. But if you, by micro Raman spectroscopy, just focused on this grain, what you would find is that the grain actually consists of two phases, because clearly there's rutile, right? So you see the bands at rutile, right? They correspond right here. But then you also see peaks showing up that you can attribute to the anatase. So what this is a grain that happens to have both phases within it. So again, just a reminder that sensitivity to crystal structure, and if spatial resolution is important to you and you need to resolve on a microscale different crystal forms, then micro Raman spectroscopy is one way to do that. Now we've talked about inorganic compounds. What about organic compounds and so-called molecular crystals? Well, here are Raman spectra of two forms of acetaminophen, also known as paracetamol. And if you look at the spectra, they look fairly similar, as you might expect, because they're the same compound. However, if you look particularly in the low frequency region, you see that the band structures are different. And even in the high frequency region here, around 1600 wave numbers, you can see some differences in these bands. Now, having said that, it's not enough to just take relative intensities to be able to differentiate the forms, because that doesn't do it. You can still have effects due to the orientation of crystals, in particular single grains, relative to the incident laser polarization. So what you really need to do is you need to be focused on, no pun intended, but you need to pay attention to, let's put it that way, the peak positions. And so if you have two compounds that are of identical crystal forms, then you're going to have all the peaks will be at the same peak position. Take like these two right here. However, not all the peaks match up and are not at the same peak position. And so even in the high, for example, 1327, 1324, all right, so there's a 3 wave number shift between these two peaks, okay? And also you've got, if you look at these two peaks over here, we've got a band at 1619 and 1611, and that's probably, these peaks probably correspond to these peaks right here at 1609, where this one is shifting to a lower energy, but this one is shifted by 6 wave numbers to a higher energy. So we can differentiate, even in the higher frequency portion of the spectrum, the different crystal forms. In the mid region, we can also find peaks where there's a big difference. So here we've got a 12 wave number shift, pretty substantial. Okay, so in some cases you have no shift whatsoever. Other cases very small, 651, 652. But the key is, in all cases throughout the spectrum, it's the peak position and therefore the need for spectral resolution to differentiate the crystal forms. And finally, the low frequency region of the spectrum, sometimes called the ultra low frequency, going from, let's say, 10 wave numbers, 10 reciprocal centimeters out to 250. That's where you see the greatest differences depending upon the crystal structure and how these molecules are packed in the unit cell. So, same chemical compound, different crystal form, and Raman spectroscopy is then useful for differentiating polymorphs. Now let's look briefly at liquid and headspace Raman spectroscopy, and particularly the interactions that we see, the molecular interactions, including hydrogen bonding. So here's a nice little apparatus which you can attach to one of the openings on the nose piece for the microscope. So replace a microscope objective with this macro sampler, and the laser beam comes to a focus right in the middle of this cuvette. And so it makes it very easy to do quantitative analysis of, let's say, of solution chemistry. You can also put in this vial a very small amount of liquid and then detect the headspace if the laser beam passes above the liquid. Conversely, you can take this piece off. See, you have some set screws here. You can take that piece off and just have the laser beam come out, and you can set any object you like on the microscope stage. Here the laser beam is going inside a bottle and analyzing the liquid. And if we just move the stage, we can be focused in on the headspace gas above it. So if we look at the spectra of the headspace of beer, what should you expect to see? Carbon dioxide, and indeed we do. So I'm not going to go through the assignments of these bands or Fermi resonance and so forth, but I just want to show you how with so little background and with the appropriate spectral resolution, here we've got 0.9 wave numbers, it's the full width half max of this peak. You can readily perform vapor phase headspace Raman spectroscopy. And so you can see the oxygen in the headspace of the beer sample as well. Now the beer fluoresces, so if we want to look at the molecular interactions of CO2 and water at that same excitation wavelength, 532, that's a better choice. So here again is our headspace Raman spectrum of CO2 and oxygen. And now look at the CO2 bands that are in the sparkling water. Notice the shift here. You've basically got, what is this, like an 8 wave number shift and a broadening of this band because the CO2 is now in the water. And so same for the 1285 down to 1273 wave numbers. So now you have stronger molecular interactions of the CO2 with the water. And so the magnitudes of those shifts and the broadening of the bands will give you an indication of the types of molecular or the strengths of the molecular interactions that you see. In fact, for really strong molecular interactions, nothing beats hydrogen bonding. So if we look at ammonia, all right, so here's the liquid ammonia spectrum. So we're basically seeing these broad peaks here is from water. Okay, so that's OH stretching from water, this and this. And then this peak here is the NH stretch from the ammonia. And then in the vapor phase, the headspace above the ammonia, you see a significant shift, 3314 to 3340, but not nearly as big of a shift as you see for the OH stretch, where both of them are unresolved, but the peak is at 3659. So what this is showing you is that the hydrogen bonding in water is substantially greater than hydrogen bonding and other molecular interactions of ammonia with water. All right, so again, Raman spectroscopy for both liquid and headspace, but also probing molecular interactions. So if you look at methanol, again, here's the OH, the symmetric and antisymmetric stretches of OH well resolved in the vapor phase, out at way out at high energy, 3684, 3697, and then a substantial shift and broadening because of hydrogen bonding in liquid methanol, right? Now, you also see the effect of the interactions in the headspace versus the liquid in the CH stretching region, but of course, they are not as different as in the case of the hydrogen bonding, because these molecular interactions in going from the vapor to the liquid phase are not nearly as great. So that was a little discussion then about vapor phase, liquid phase Raman spectroscopy, and the study of molecular interactions within a solvent. So you can think of perhaps other ways in which you might want to study the structure, the interactions of some analyte in a solvent for other systems. Now we'll talk about briefly Raman spectroscopy of polymers, and we'll briefly discuss aromatic polymers, one in particular PET, and then stretched polypropylene. Well, polymers are, I'm sure most of you are aware, they're just long chain repeating units of organic compounds. And we're using these cartoons here, if you will, to indicate, let's say, a completely amorphous, disordered polymer, one that might have some orientation, perhaps induced by stretching or tentering, and then maybe even a crystalline form that's been heated and cooled in some form. So the thing is that Raman spectroscopy can give you information about these different kinds of solid state structures of the polymers. So what kind of information can you get from polymers? Chemical identification. I mean, basically differentiate different kinds of polymers. The tacticity of them through side group positioning in the polymer, morphology, such as orientation or even crystallinity. And how might they be used? Well, to identify contaminants, composition of copolymers or blends, the strength, the elasticity, dyeability, other physical properties of the polymers that relate to the chemical bonding and the solid state structure, and to study drug delivery, how well solvents are or how well drugs may be soluble in a particular polymer, as well as barrier films. Okay, so here are three spectra of aromatic polymers: Kevlar, PET, polystyrene. So they're similar, as one might expect. You see certain bands associated with the aromatic functions here, and some of them are labeled. So here's an aromatic band, here's an aromatic band. You've got a carbonyl band from the PET, but they can all be readily differentiated by Raman spectroscopy in a manner that is, again, quite complementary to what you might see using infrared absorption. Now, one point that I want to make about the PET is that when breaking down sort of the structure of PET and assignment of modes, you've got bands in here which can be assigned to the glycol modes. This is a ring stretching band. This band here is a carbonyl band, which, as it turns out, is very sensitive to ordering and, in particular, crystallinity. So the more crystalline the PET, the narrower this band is. And so for many years now, people have used Raman spectroscopy, where X-ray diffraction might not have been convenient, to to characterize the degree of order or even crystallinity in PET just by the well-characterized carbonyl stretching band that you see at around, let's say, 1730 wave numbers or so. And we'll finish up with the polymers by just showing you the difference between stretched and unperturbed polypropylene. So the blue spectrum is just as is, if you will, polypropylene as prepared or molded, and a film at that. And then the red spectrum is from that same polypropylene that has been stretched. So same sample, but it's been stretched. And so what happens? You see in the spectra overlaid, big changes in relative intensities. And as we'll see in a little bit, some changes in peak position. Now I've labeled the bands at 315, 835, and 992 because they're the bands that show very little change in intensity from unperturbed to the stretch. So you see most of the other bands are affected as a result of the stretching. So I just want to quickly go through from the low to the high region of the spectrum blown up. Here you see a shift to 391 wave numbers, so it shifts to lower wave numbers as you might expect for the stretched polymer, because as you stretch the polymer, you're essentially pulling the bonds apart, and so some of the bands, some of the vibrational modes will be sensitive to that, and so you see a change not only in the relative intensity, but the peak position commensurate with the stretching of the bands. Once again, here's a shift to, in this case, 1 wave number. So these shifts can be small, but again, that's where the spectral resolution of the spectrometer comes in to be able to detect that. Differences in relative intensities, but also differences in the peak positions. And then going finally out to the top of, or the high end of the fingerprint region, you can still see some small differences in the peak positions. Here's a 2 wave number difference, and of course differences in the relative intensities. So stretching of polymers and tentering and strain in the polymers, that's something that you can access and characterize with Raman spectroscopy. All right, so let's conclude then with a discussion of particle finder, which is a very nice method for performing chemical specific particle size distribution. So particle finder allows you to use basically microscope optics and visual technology tools, imaging tools, to be able to characterize the particles, their location, their size, shape, uh, you know, um, their ellipticity, circularity, things like that, all by the imaging portion. What Raman spectroscopy does is then to add to the characterization that you do through the imaging is to provide chemical analysis so that you have chemical specific particle size distribution metrics when completed. So how does this work out? You start by obtaining images by either transmitted or reflected white light, and you can do so at very high spatial resolution by montaging the image. So you can even see a kind of a checkerboard pattern in here. So let's say you wanted to use a 100x objective. You can use particle finder such that the stage will move in a montage fashion from one area to the next, keep moving around like this, and then stitch together all these fields of view for a much larger field of view that far exceeds a single field of view of the objective, so that you have the same spatial resolution and high magnification, but a much larger field of view. So there's a montage image of a bunch of particles on a substrate. Then you use the tools in the software to locate particles that may be of interest to you, and they get automatically detected through the software and highlighted with colors, as you see. And you can then process these images using the erode, dilate, open, close fill holes, remove edge particles functions that you may be familiar with using other kinds of imaging tools and software for particle size distribution through optical microscopy. All right, once all that's done, you then end up with a table of some metrics of distribution of the centers of the particles, the areas, diameter, perimeter, the major axis, minor axis, all the things that you see on the left here for the characterization based on the imaging portion. All right. Then once you've obtained these metrics, you may want to screen some of the particles. That is to say, not examine all the particles. Maybe you want to exclude some based on either position, size, or shape. So you have those tools to be able to do that. And then once you've selected those particles that are of interest to you, you acquire Raman spectra of each of the particles. So once they're selected, the stage will then move when you exercise particle finder such that the particle falls under the laser beam, a Raman spectrum is acquired, and from that Raman spectrum, you then get chemical identification. And so, again, for the video imaging portion, you get the following kinds of statistics. These happen to be just pharmaceutical crystals on a glass slide. And you see here that edge particles were excluded, as also particles with greater than 50 square micrometers. And so we end up with these following types of statistics. That's based on the imaging portion. Now here's what your workspace will look like in LabSpec 6. So here you see the image of the particles, and they're color coded for, in this case, particles of paracetamol or acetaminophen and polymethyl methacrylate. The PMMA are these red particles. They've been identified as such by the Raman spectra because this has already been run. Raman spectra were acquired, and so the particles were then colored in the image red or green, corresponding to either PMMA red or paracetamol green. So here's the entire hyperspectral or entire spectral data set of all the particles. If you click on any one particle, the spectrum of that particle will show up here in the particle spectrum. Then you'll have some data tables and metrics below. Here's a data table that you can see which lists many of the familiar metrics for size and shape of these particles, which can be expanded. You click on this little icon here, can be expanded, and so what you see in your final results then are all the metrics that you might expect to see for particle size distribution. All right, area, diameter, perimeter, the things that ellipse ratio, the things that I've been mentioning, including a column with an image of that particle, right, for that particular particle, the spectrum acquired from that particle, and then under the ID column, a color-coded identification of that particle based on the Raman spectrum. So that's the basic operation then of being able to perform chemical-specific particle size distribution and characterization. So I guess I've just finished my conclusions with the last item by saying that. And so we'll conclude by going back to the top and say, what have we covered here? Well, we've discussed Raman spectroscopy and laser excited photoluminescence performed with the same instrument. We've shown that Raman spectroscopy is useful for differentiating polymorphs and characterizing polymers, and even a micro Raman instrument is useful for analyzing both vapor phase and liquid phase and studying the molecular interactions in either of the phases which manifest themselves in the Raman spectra. And so with that, I'd like to thank you for your time and your attention.